Good afternoon, everyone. Welcome to the Terminology Leading Practices stream at the SNOMED CT Expo 2025. Thank you to TermMed for sponsoring this stream. My name is Maria Braithwaite and I'm a senior terminologist at SNOMED International. I'll be your moderator for today's session. We'll address all questions at the end of the presentation. For our online audience, please use the Q&A button to submit your questions to the presenter. And for those of you in person, feel free to use the microphone provided in the room when the time comes. It is now my pleasure to introduce Vinicius Vanzin from Universidad de Sao Paulo, who will be presenting Large Language Model-Based Pipeline for Anaphylaxis Data Structuring and SNOMED CT Concept Mapping. Vinicius, over to you.
Hello everyone, I'm Vinicius Vanzin from the University of São Paulo, and today I'll present our work on a large language model-based pipeline for structuring anaphylaxis data and linking it to SNOMED CT concepts. This project aims to improve the accuracy and interoperability of allergy-related information in electronic health records, supporting safer clinical decisions and better research data. By the end of this session, these are the key points that you will hopefully take away from this presentation. We'll look at the challenges of documenting anaphylaxis in EHRs, how large language models can help transform free text into structured data, and finally, how our annotation tool enables experts to collaboratively build high-quality datasets for evaluation and research. This project is part of a broader collaboration between the University of São Paulo and Sírio-Libanês Hospital in Brazil. We are a multidisciplinary team that brings together clinicians, terminologists, and data scientists. Our shared goal is to advance allergy and anaphylaxis research using computational methods, improving decision support, interoperability, and data standardization. Within this larger initiative, the work I'll present today focuses specifically on the standardization and annotation components of the pipeline. Let's take a look at the scale of the problem. About a third of patients have at least one allergy documented in their EHR, yet the accuracy of these records is often poor. Roughly 10% of fatal adverse drug events are allergy-related, often because of incomplete or inconsistent information. Improving the structure and reliability of allergy data directly contributes to preventing medication errors and repeat exposures. Anaphylaxis is the most severe form of allergic reaction. It develops rapidly and can be life-threatening if not recognized immediately. Its lifetime prevalence is estimated between 0.3 and 5%. Accurate documentation of the trigger, timing, and symptoms in the patient record is essential for safe prescribing and alerting systems. These criteria on screen show how variable the clinical presentations can be, reinforcing why structured data is so important. Unfortunately, much of the allergy information in EHRs still appears in free text notes. These notes are often inconsistent, fragmented across systems, and difficult to reuse for research or clinical decision support. Here you can see a typical example, a description of an insect sting reaction recorded entirely in narrative form. This gap between clinical language and structured information is exactly what we aim to bridge. Advances in natural language processing and large language models now allows us to extract structured information from text at scale. By aligning those outputs with standards such as HL7's FHIR, which defines the data model, and SNOMED CT, which provides the terminology, we can turn free text notes into interoperable, machine-readable allergy data. Our overall goal is to produce high-quality, standardized data compatible with decision support systems. To illustrate this transformation, here is a practical example. On the left, we have a free text note describing symptoms after an insect sting. Through the pipeline, those details are extracted as discrete entities, the allergen, manifestations, and exposure route, and then represented as a FHIR-compliant JSON document. This conversion from natural language to structured data is what enables interoperability downstream. Here's an overview of the pipeline. It is a multi-stage process. We start with unstructured clinical text, perform entity extraction, then map those entities to SNOMED CT concepts, and finally, generate a complete FHIR-compliant resource. The architecture is modular and agentic, meaning each component can invoke specialized tools and operate independently. That flexibility lets us refine each stage without affecting the rest of the system. The first stage in the pipeline is entity extraction. The model identifies key elements such as substance, manifestations, and exposure route mentioned in the text. Output generation is guided by the official FHIR schema to ensure that each extracted field aligns with the expected data types. We also use structured output and few-shot prompting techniques to minimize hallucinations and increase consistency. This produces a structured draft that serves as the foundation for the next step. Next, those extracted entities are linked to SNOMED CT concepts. The mapping relies on both external terminology service APIs and vector-based similarity methods to identify the most appropriate concept. This grounding step ensures that model outputs are consistent with standardized clinical vocabulary. As you can see in the example, the term insect sting is normalized to the SNOMED CT concept insect venom. SNOMED CT is particularly well suited for this task. It provides comprehensive coverage of allergy-related concepts, whether drug, food, or environmental triggers, and its granularity allows us to distinguish between closely related reactions. Each mapped concept is inserted directly into the FHIR allergy tolerance structure, according to the schema's terminology bindings. This diagram shows the internal flow of the mapping process. First, a query is generated for the extracted entity. Then, the system retrieves candidate concepts from a vector store or terminology service. Next, these candidates are evaluated by the LLM-based normalization agent that ranks them by contextual similarity. Finally, the selected concept is inserted into the resource. This retrieval-augmented approach combines the reasoning ability of LLMs with the grounding of external terminologies. Once entities are mapped, the information is structured into a FHIR allergy intolerance resource. This JSON-based format is interoperable across FHIR-compliant EHR systems and captures relevant details such as substances, manifestations, and exposure routes. We also add onset information for anaphylaxis, which is critical for identifying acute reactions. This structured output can then be validated, shared, and reused in other clinical and research systems. Here, we illustrate the modular architecture that supports the entire pipeline. Each stage, extraction, mapping, or resource generation, operates independently and can invoke specific tools such as vector stores, terminology services, or embedding models. Each step can also correct intermediate errors before they propagate to later stages. This architecture is designed for experimentation and reproducibility. It allows us to compare different LLMs and test various APIs. While the pipeline can produce structured data automatically, we still need expert annotated datasets to evaluate and improve it. These datasets serve as ground truth for benchmarking. Creating these datasets requires close collaboration between clinicians and terminologists, ensuring both clinical validity and terminological precision. The need for structured annotation is what led us to the development of our next component, the annotation tool. The annotation tool is a web-based, form-driven interface that automatically generates forms from the FHIR schema. It allows users to view and edit system-generated records without dealing with raw JSON. The main goal is dataset construction, enabling experts to create high-quality reference data for research and model evaluation. It is built with usability in mind so that clinicians and terminologists can collaborate effectively within the same environment. We designed the tool to be intuitive and lightweight. Clinicians can work through a familiar form interface, while the system handles the underlying schema automatically. Real-time editing, saving, and progress tracking are built in. Role-based permissions support different workflows. For instance, a clinician focusing on reaction details and a terminologist refining concept mappings. Here, you can see the full annotation workflow. It starts when the pipeline generates a draft FHIR resource from the clinical text. Clinicians review and adjust the clinical fields. Terminologists refine the SNOMED CT concept bindings. And finally, the record is marked complete for inclusion in the dataset. Every record is logged with author attribution, which provides transparency and traceability throughout the process. Let's walk through a brief example. A patient note describes fainting and seizures following an insect sting. The system generates a preliminary structured record with placeholder codes. Clinicians verify the manifestations and allergens. Terminologists then replace the placeholders with the correct SNOMED CT concepts. Through this process, we move from unstructured text to a validated interoperable data entry suitable for model evaluation. This tool enables systematic, collaborative annotation at scale. It helps build benchmark datasets for evaluating our pipelines and reduces the manual effort required to structure and map data from scratch. The resulting datasets are more reliable and easier to reuse for both clinical research and terminology studies. Here, we can see the list view of the annotation tool, which provides a broader project-level perspective. Each row is a clinical note or record to be annotated, showing key information such as the current annotation status, the assigned reviewer, and progress indicators for completion. This interface allows project coordinators to track ongoing work, balance assignments between clinicians and terminologists, and quickly identify which records still need review or validation. Clinicians, terminologists, and data scientists can work on the same artifacts with a shared understanding. The framework supports evaluation of NLP pipelines and contributes reusable resources for concept mapping and data structuring research. To summarize the key points, structured allergy data is essential for patient safety and system interoperability. Large language models automate much of the extraction, while SNOMED CT provides the semantic foundation of standardization. Our annotation tool enables the creation of high-quality datasets, an important step for evaluating and refining these methods. And importantly, collaboration across clinical and technical domains ensures the resulting data are meaningful, accurate, and usable. Finally, both the code and curated datasets will be available publicly in the future. Thank you very much for your attention. If you'd like to discuss this further, please feel free to reach out. Thank you.
Thank you. Thank you, Vinicius. We will now begin questions. Vinicius will be joining us online from Brazil. As a reminder, if you're in the room, please use the microphone to ask your question so that everyone can hear clearly.
Hi, I'm Stefan Schulz from the University of Graz, and my question is about the gold standard you are creating. Do you have results about inter-annotator agreement? Because I can imagine taking that allergy example, for instance, somebody has an allergic a reaction after taking a drug containing ampicillin, and then one annotator annotated with amoxicillin substance, another one with product with ampicillin, another one annotated with amoxicillin trihydrate, another one with amoxicillin sodium, etc. So normally you need annotation guideline to streamline these annotations and avoid these disagreements. Which are your experience with that?
Thank you for your question. Yeah, we are currently building the ground truth dataset, and the annotation tool supports collaborative editing, real-time editing, and we are also evaluating multiple rounds of review to guarantee inter-annotator agreement also. So yes, that is a main concern in our case. Allergy data requires precise annotation. So yeah, that is a valid concern. We are dealing with that at the annotation tool level.
Hello. So this is Veronique. I also have a question. I was wondering what the impacts would be for like the clinicians in practice, and as a validation process then more, because I am wondering in practice, yeah, there's an administrative burden and stuff, and they need to validate these allergy outputs, but how do you distinguish this between the relevance for medication or then indeed food allergies or other stuffs? So yeah, what's your experience on that?
So yeah, as I mentioned before, this project is part of a larger initiative in our research group. And the described pipeline actually comes after a classification system, which analyzes the clinical text and determines whether it is really anaphylaxis related. And then the clinical notes move to this structuring pipeline that I just described. So we are actually building an entire decision support framework to help clinicians in detecting anaphylaxis in clinical text. It's not just the structuring pipeline.
Okay, thank you.
Are there any more questions in the room? Not seeing any. I've got one more for you. What challenges were encountered during the development of the annotation application, particularly in aligning clinical usability with technical requirements like fire compliance?
Okay, so one of our primary design considerations was to develop an interface that would not overwhelm domain specialists. So the form displaying fire resources includes only the information necessary for each user role. For instance, from a clinician's perspective, as long as the correct terms have been extracted from the clinical note, it is unnecessary to display terminological codes. So early in development, we determined which subset of fire fields was essential to encode the information in the clinical notes. And the concept mappings are shown only to terminologists. In addition, several terminology bindings that are merely recommended in the fire specification are enforced in our implementation to constrain the concept set to a manageable and meaningful subset of codes.
Lovely, thank you. Are there any further questions? No, then that concludes the session. To our online delegates, you're welcome to remain here for the next presentation in this stream, or you may navigate to another session via the event lobby. Thank you, Vinicius, for joining us and for that excellent presentation.
Thank you.